what does make things spin in general? You make things spin every day. When you enter this room, you make the door spin. When you're leaving this room, you make the door spin. So imagine this is a door. So a hinge which holds it. So I can move it by applying a force anywhere. Now let's say there's someone, a strong guy, who doesn't want me to leave this room. Well, I can make him move if I apply a certain force. Oops, don't kill. Let's see what force should I apply. Two kilograms, 3 force. So this weight totally has mass of 4 kilograms. We actually know that if I want to pull it, I have to apply certain force. If I pull it with constant velocity, this is force applied compensates kinetic friction. So this is the amount of force I need to apply to it to move it, about 12 newtons, right? So how can I make 12 newtons? Let's say I'm going to pull or push on this door, not at the doorknob, not directly there, but some closer to the middle. It's already 12, it's not moving yet. It means here I'm applying 12, but here it's not yet 12. To move this point must apply 12, because that's what we saw before. So to make 12 here, turns out I have to keep like 15 there. What if I, well, you will not be able to see it. What if I move it even farther away? Farther away, in that case, here, I have to apply about 20 newtons to generate same 12 there. So it's not just force, that's the first point. It's also the location. So we need something related to force and location. Actually, there is another interesting experiment. Let's say I apply force here. Again, come on. So again, first time, oops, I bent it. Okay, so slides about 12. Now, second time, different angle. And if I change the angle to generate 12 newtons there, you see, I need to apply here at a different angle, much stronger force. So the angle also matters. Why? Because the force is a vector. When I push in this direction, the force which points at the hinge doesn't matter at all. This force, or this component of this force, cannot make rotational motion. So only the component which is perpendicular matters. So even not the whole force, only a component that perpendicular to it matters. Well, there is another example which I want to show quickly that it's not just about force, it's also about location. It's a standard kind of old-fashioned lab experiment. If I want to keep this rod horizontal, so if I apply a force here, I see this number, what is it? About 20. What's going to happen if I want to keep it horizontal? If I apply a force at a different location, I have to apply a stronger force to compensate actually, well, force of gravity acting on this rod equals mg. So the force of gravity doesn't depend on my force. So again, it's not just force, it's where it is applied and also how. If I change the angle, the force changes. Again, this force has two components. The component which points toward this hinge doesn't do any rotational action. Only the component that's perpendicular to it responsible for rotation about this point. Well, we call it hinge or axis of rotation. Many experiments like that tell us that we need to use a variable that is a combination of force, distance, and angle. So let's say I'm applying a force like that. This is a hinge. We can break the force into two components. Natural symbols are like that. A component that is parallel to what? Well, this is the hinge or axis of rotation. People call it O. This is where my force is being applied. That's a specific physical location. This is a point, and force is applied here. That is why this point has a name, the point of application of a force. Now, there is a line that connects 2 points. Between any 2 points, we can always draw a line. Well, this line has no special name, but it exists. Relative to this line, every force has two components. One component that is parallel to this line, and second, that is perpendicular. This component does not matter. Also, distance matters between the axis of rotation and point of application. So this is what people have invented. A product matters. And because it matters, people gave a name, torque, and a letter, usually a Greek letter tau. And this is an official definition of the magnitude of a torque. What do we need to calculate to magnitude? 1 point, axis of rotation. Second point, the point of application of a force. The force itself, the distance. The component of a force that is perpendicular to the line connecting dots, and then you can write this. So you see, it's kind of complicated definition. It involves several important steps. If you make a mistake with one step, the result will be wrong.